Okay, so your book's on your desk there, Andrew, and we're on page 635. You're welcome.
Do you happen to see Eve on the way? Last week in the bathroom, she just texted me saying, "Where the hell are you?" Tell her we're in the classroom.
I already told her.
6:35. What should we all say when she walks in? We have to say something.
Hello, Eve. Happy Star Wars Day. All right, so anyway, 13.1, here we go. All right, how is the graph of g of x equal to a times b to the x minus h plus k, where b is greater than 1, related to the graph of f of x equals b to x? Okay, so, sorry? There will be logs in this, yes, okay. All right, so David, I want you to go back to that seat until it's time when I get you guys your homework and stuff like that, but not right now. Oh, okay, well you can sit here then if you want to. Okay. So, exponential, that word, right, you see the word exponent in there, okay, and so we call these things exponential functions, okay, when they're in the form f of x equals b to the x, where this number b is called the base, all right, like in an exponent, right, when you have like, when you have like 2 to the third, that number 2 is called the base of the exponent, and then 3 is the exponent, or the power there, okay? And so the exponential idea is that our variable x is in the Eve. So good to see you. Sorry
you just earned yourself a referral.
No. But your book, we went and got books, Eve. That's where we went. So there's your book, okay? And we're on page 635. So anyway, so the new thing here, or the twist, or the change, is that our x is in the exponent. We've seen other functions where x is the base, right? Like x squared or x cubed, right? And we know those have different kinds of graphs. But then when we change things and put x in the exponent, that can really affect things too. Okay? And so one of the key things here to point out is that there is no single parent exponential function, because each choice of the base b determines a different function. And so it's not quite so easy to transform these as it was in the past, or to identify the different transformations and stuff like that, because the base is also changing, the b, okay, letter b. So we're going to complete an input-output table for each of these kind of exponential functions here. We have 2 to the x, and we have 10 to the x. Okay, so f of x equal 2 to the x when x is negative 3, so we're going to have 2 to the negative 3. Okay, and if we remember here, a negative exponent, we can make it, a fraction, 1 over 2 to the third, which I'm running out of room here, but that's because I'm writing it out, equals then 2 to the third is 1/8, so it's 1 over 8 there. Okay, so 2 to the negative 3 is the same thing as 1 over 2 to the positive 3, which is then 1/8. And so we can kind of keep doing the same thing here then. 2 to the negative 2 will be 1 over 2 squared, which is then 1/4. Okay, 2 to the negative 1, that's going to be what? 1/2, or 1 over 2 to the 1, which is just then 1/2. Okay, what about 2 to the 0 power? 1, right, yeah, it's just 1. Anything to the 0 power is 1. Good, you guys remember that? Okay, how about 2 to the 1? What's that? Just 2. 2 to the 2? 4, and then 2 to the third? 8. Okay, so you can see those values there. Oh, sorry, I went off the screen. There you go. Okay, likewise, we do the same thing with 10. So yeah, so 10 to the negative third is 1 over 10 to the positive 3, which again, 10 to the third, 10 times 10 times 10, you just keep adding zeros, and you get 1/1000th, as Greg said. And so then 10 to the, oops, I don't know why I put a negative 10 there, my bad. And then 10 to the negative 2, 1 over 10 squared, which is 1/100th. And then it's going to be, well, 1/10th. And then 10 to the 0, oh, sorry, I'll write that. And then 10 to the 0 is 1. 10 to the 1 is 10. 10 to the 2 is 100. And 10 to the third is 1000. Okay. In the first table, right, every time we go up a power, our answer multiplies by 2 more. So 1/8 times 2 is 1/4, times 2 is 1/2, times 2 is 1, times 2 is 2, times 2 is 4, times 2 is 8. Same thing here, except now we're multiplying by tens. Times 10 is 1/100th, times 10 is 1/10th, times 10 is 1, times 10 is 10, times 10 is 100, and then times 10 again is 1000. Okay? So there's our table. And so let's look at what these things look like when we graph them. Okay? Oh, sorry. Okay. And again, we'll look at what these things look like when we graph them now. So it gets kind of out of control pretty quick here, right? If you look at the 10 to the x, we have 1/1000, which is really hard to graph, and then we also go all the way to 1000, and that's just within a couple numbers here, right? Just 6 numbers, and we 7 numbers, and we end up getting to like over 1000, or up to 1000. So let's try and graph these, see what they look like. All right. So let's see here. When x is -3, we got 1/8. So let's see here, negative 1, 2, 3. 1/8 is kind of like, you know, kind of just barely off the axis there. -2 and 1/4. So that's going to be like a quarter of the way up. So something like that. -1 and 1/2. So that's going to be halfway up there. And at 0, it's 1. So that's pretty easy to graph. There's 0, 1. And then at 1, we're at 2. At 2, we're at 4. At 3, we're at 8. And it just barely fits there. Okay, so you can kind of see the graph. Okay, so there is our graph. Okay, so you're just plotting those points, what we get there. All right, same deal here. Let's look at the next one. Okay, we'll do the same thing. We're going to plot some points here. So again, at -3, it's 1/1000. So that's like almost impossible to graph. We'll just like graph it really low, but almost 0. -2, 1/100th, also again really small. -1, 1/10th, also again really small. And then finally 0, 1, that's easy to graph. Okay, and then at 1, we're at 10, which is, well, there's 8, there's 9, 10 is going to be like up here. And then 2 and 3 and 4, well, it's off the graph. And so it's kind of like very steep. And then it flattens out very quickly, too. Okay, so something like that. Just increases really quickly. All right. So there are our graphs. Questions so far on any of that? Okay. So let's take a look at the next page here, and we're asked to describe the domain of each function and then also its range. Okay. So if we look here, what does it look like the domain of this function or this function might be? -infinity to infinity. Yeah, all real numbers. Okay, there's no real limits, and for both of them, right? They both kind of go forever in both directions. Okay, they're going to get really small, but yep. So we can say here x such that x is, you know, just a real number, and same thing here. X is a real number. Okay. What about the range? Is the range going to be all real numbers here?
No.
Doesn't look like it, right? What does it look like is the lowest possible y value here?
0.
Yeah, and does it look like we actually get to 0?
No.
Right, it looks like we are approaching 0, but we don't actually get there, which would indicate what kind of asymptote do we have? Potentially a horizontal asymptote there at 0. So yeah, we don't actually get there, but we get awfully close. Okay, and so for our range, we'll say it's y such that y is greater than 0. We're going to use inequalities here, and again, y is greater than 0 for both of them. Okay, so y is greater than 0, y is greater than 0. What about y-intercepts? What are the y-intercepts for both graphs? 1, right? Yeah, at x value of 0, they both have 1, which makes sense, because again, 2 to the 0 is 1, 10 to the 0 is also 1. So the y-intercepts there are 1 and 1. Okay? And then what is the trend of each function? So in both f of x equals 2 to the x and p of x equals 10 to the x, as the value of x increases, the value of y, what? Increases or decreases?
Decreases.
Let's take a look. As x increases, what happens to the values of our y values here?
Increases.
It increases. Yeah, it's increasing. Okay, that's exactly right. So we're going to get increases. Okay, y increases. Okay. So then, will the domain be the same for every exponential function? What do you guys think? I mean, will we have the same domain? Will it always be all real numbers?
Yep.
For the most part, yes, with exceptions. So, for example, if our number is negative, then it won't be all real numbers because, for example, you can't take the square. You can't like have -2 to the 1/2 power. So we have to be careful with that. But as long as b is positive, yes, any number is acceptable up there. Okay. And then we'll see more about the range. Range is a little bit harder to imagine, I would say. And the y-intercept, okay, yeah.
Our horizontal asymptote will be 0.
Yeah, so for a form of this, so for this basic exponential function, the range will always be the same. It'll always approach 0, it'll always have a horizontal asymptote at 0, and then it'll go off to infinity too, so 0 to infinity. So yes, it should always be the same. And then will the y-intercepts always be the same? Again, for this basic one, yes. Because again, whenever you raise something to the 0 power, it's going to be 1. So the y-intercept should always be 1. Okay? So now we're going to talk about combining some transformations here. Okay? So, a given exponential function, g of x equal to, and now you see we added an a, we added an minus h with the x, and we added a plus k. Now that h and k should be super familiar. What is the h going to do for transformation-wise? Shift it, yeah, left and right, and the k is going to do what? Up and down, and then a is going to be a stretch, vertical or horizontal, depending on how you want to, determine it. Okay, so that's exactly right. Yeah. Oh, and also a can affect whether it's reflected over the x-axis or not because of its positive or negative. Okay. So we can use the parameters in g of x equals b to the x minus h plus k to see what happens to two reference. Oh, that minus h should be up with the x there. That's a typo, but anyway. To see what happens to two reference points during a transformation. So 2 points that are easily visualized on the parent exponential function are 0, 1, so that's our y-intercept, and then also 1 comma b, so it's like the power of 1, our b to the power of 1 there. So in a transformation, the point 0, 1 becomes h comma a plus k, so in other words, we shift it left or right depending on where it was, and then a plus k, and then 1b becomes 1 plus h, and then ab plus k. Okay, so again, that point also changes. And so the asymptote y equals 0 becomes the y equals k. Again, if we shift things up or down, that horizontal asymptote at 0 is going to shift up or down too. Okay, so let's look here. So again, here's those graphs of 2 to the x and 10 to the x, just so we can have, and we show them with the reference points. There's 2 to the x's reference point at 0, 1, right? It always has that reference point at 0, 1. And then at 1, the x value 1, we get our y value 2. And then likewise here, it's got a reference point 0, 1, and then the 1, 10, well, it's off the graph, so that's why they didn't show that one. But up here somewhere is like the 1, 10. Okay, so two reference points here we're going to focus on. The y-intercept, where that shifts, and then also the first power. 2 in this case because it was 2 to the 1, and 10 in this case because it's 10 to the 1. Okay, so we look here, we're going to state the domain and range, okay, and then identify the new values, but they already have the new values for us, so, oh well, I guess they've already got it here. So anyway, we can see here, for example, okay, what kind of transformations can we see just from this graph right here? What's going to happen? Okay, so it's going to go right 2, up 1, okay, and then but then we also have a reflection of negative 3, so it's going to reflect over the x-axis and then stretch by 3. Okay, so you can look at the graph here and see, okay, there's the graph of it. Okay, so again, this is a transformation of 2 to the x. So there's our original function 2 to the x. You can see that our y-intercept gets shifted right 2 and up 1, but then it also reflects over the x-axis. So it was right 2 up 1, but then we get multiplied. Oh no, wait a minute. So right 2 up 1. Sorry, it was here. Sorry, it was here. Right 2 up 1, and then reflecting over the x-axis, it goes down to this point right here. Okay. Again, there was our y-intercept, right? Right 2 up 1, and then it reflects down to there, and that gets us our new point right there. Okay. And then likewise, our other point here, the point 1, 2, okay, we shift it, let's see, it was at 1, 2, shift right 2, 1, 2, and then up 1, okay, but it's actually going to go up 3 because of this there, and then it reflects down to the negative 5. Okay, so that's a little bit funky here, but there's some calculations we can do too. Okay, so anyway, so if we look at the domain, we can analyze that pretty easily. You can still see it's negative infinity to infinity, and then the range here, because of the reflection, you can see what's the highest range value that we have in our graph. 1, right? It goes up to 1 and then down to negative infinity. So you can describe that as y such that y is less than 1, or if you want to use interval notation, you can also say like, negative infinity to 1. We don't get there, that kind of thing too. Okay. So examine the function here and identify the parameters. So a equals negative 3 means that the function is reflected across the x-axis, because of negative, and then vertically stretched by a factor of 3. And then h equals 2, the function is translated 2 units to the right, so we got that. And then k equals 1, so the function is translated 1 unit up. Okay? So the point 0, 1 becomes h, so we have to shift it right 2, so our x-coordinate 0 becomes now 2. And then a, okay, which is negative 3 there, and then plus k. So negative 3 plus 1 gives us a negative 2. So it's 2, negative 2. Okay, that's that point. And then here, 1b becomes this other point, 1 plus h, and then ab plus k. And then we simplify that, and there's our other reference point. Okay, and then we have our asymptote here too, y equals k, which is 1. Okay, that because again our asymptote shifted up 1. Where is it? Right here. Asymptote was at 0, but it shifts up 1. Okay, so that's a lot. Let me see here if I can come up with a better way of us doing this, because that's, I think, kind of crazy for us to do. So instead, let me think about it this way. What I think I'm going to have us focus on, because that's a lot of things to concern ourselves with. Instead, what I might have us do is just worry about shifting things up and down correctly, and then we'll maybe just pick some x values, plug it in, and get some matching y values. So we'll use our calculators to help us with this. Okay? So you may want to have a calculator handy. Okay? Does anyone need a calculator to borrow? Anyone need a calculator? Yeah. Okay. So let's make this a little bit easier for ourselves. All right. So examining this function right here, we can see that our graph is going to be shifted, right? So the a is 1.5, so the function is going to stretch vertically by a factor of 1.5. H, okay, is equal to 3, so the function is translated 3 units to the right. There's the x minus h, and then the k is negative 5, and so the function is translated 5 units down. Okay. I'm not going to worry about having us transform these points, because I think that's just a little bit trickier than what we need to worry about. So instead, we'll go to our graphing calculators here. Okay. And what we'll do is we'll just graph this function using our graphing calculators. So here's how you type this in, right? You're going to type 1.5, parentheses, and then 10 to the x minus 3. Now, my calculator has the pretty type. So the exponent is very clear here, what's in the exponent. If you don't have the pretty type on your calculator, let me just show you an example. Okay, you have to be a little bit careful about how you type this in. We'll do 1.5, parentheses, 10 to the, and then when you do that exponent there like that, you want to open another set of parentheses so you can get the entire quantity of x minus 3. Okay, see how I have that there? It's to the, and then the x minus 3 in parentheses, and then I closed it, so that means it's just 10 to the x minus 3. I'll close that parenthesis, and then I have the minus 5. Okay? So that's how we set that up. All right, are we all good with that? We'll make sure we can type this into our calculator accurately here. So we press graph. Okay? We can see there is the graphing calculator's version of it. Okay? So, where is the horizontal asymptote for this graph? Where's that horizontal asymptote? What value? At negative 5, right? You can count here, right? 1, 2, 3, 4, 5. So it went down 5. where else can we see in the function that our horizontal asymptote shifted down 5? Where can we see that here? Where does it show up?
K value.
Yeah, the k value, the negative 5. Okay, again, normally the horizontal asymptote is at 0. It shifts down 5, so our horizontal asymptote is at negative 5. So if you look here on the graph that we're supposed to sketch, okay, there's 0, that's negative 2, that's negative 4. So negative 5 will be halfway, so we can just kind of sketch a horizontal asymptote in there at negative 5. Okay. Just like that. There's a horizontal asymptote. And then let's get some points here. Now it's kind of hard to read these points, but if we press second graph, we can go to our table. Okay, and actually I'm going to press second window. Okay, so you'll notice my table is blank, and that's because I pressed second window, and that takes me to this table setup menu, and I changed my independent variable from automatically filling in for it to wait to ask me. And I like to have it ask. So if you flip over and hit ask, it'll make your table blank, and now you can type in whatever x value you want. So for example, you can type in x value of 0, and we get negative 5, or well, negative 4.999. So at 0, we're at negative 4.999, so that's like really close to that. Okay, so we can plot that point there. If I type in 1, I get negative 4.985. So at 1, which is halfway here, negative 4.985, so it's still right down here, pretty low. Okay, let me try 2. 2, I get negative 4.85. So here's 2, negative 4.85. So again, still pretty low. Let me try 3. I think it gets better here. There we go. At 3, I'm now at negative 3.5. So here would be 3 and negative 2, 3.5 right here. And let me try 4. 4 gets me to 10. So 4, 2, 4, 6, 8, 10. There's my other point. So you can see it's going to kind of come down there and go like that. And again, just approach that y, the horizontal asymptote. Okay? So there's that. Okay. Let's try another one here with this graphing calculator. Okay, let's try number 4. I don't really like these ones that have a base of 10, so we'll do number 4 and then we'll skip number 5 because it's got a base of 10 as well. It's too big. It's too much. Okay. So here we'll graph this guy. All right, again, let's retype this in our calculator here. So we'll clear out the old y1. And we'll do 4, parentheses, 2 to the, again, parentheses, x plus 2. Okay, close both sets of parentheses there. And then minus 6. Okay, before I go and graph this, can anyone predict what the horizontal asymptote is going to be just based off of the equation here? Negative 6, right, it's going to shift down 6. So we can go ahead and draw that into our graph here. There's our horizontal asymptote through negative 6. Okay, just like that. All right. And then again, we'll just pick some more points. Okay, you can kind of see what's going on with my graph there. So let's see if I type in, well, if I type in 0, I'm at a y value of 10. 10 is off my graph there, so I don't want to pick that. And it looks like if I do 1, 2, 3, 4, those numbers are all way too big, right? So I'm going to have to go backwards. Let me try negative 1. Aha. At negative 1, I'm at 2. So negative 1, 2. And then let me try negative 2. Negative 2, I'm at negative 2. And let me try negative 3. Negative 3, I'm at negative 4. This is working out pretty nicely. And let's try negative 4 and see what happens. Negative 4, I'm at negative 5. Okay. I'll try negative 6. Actually, I missed negative 5, sorry. Negative 5, I'm at negative 5.5. So negative 5, 5.5. Okay. And then at negative 6, I'm at negative 5.75. Sorry, my book is going away from me here. Okay. At negative 6, I'm at negative 5.75, it's like right there. And I just keep getting closer and closer and closer to that horizontal asymptote. And so you can kind of sketch the curve. in here like that. Okay? And so there it is. Okay? There's a sketch of the graph using our graphing calculator that helps us. And again, there's that horizontal asymptote that we approach. All right? So, questions on any of that? Questions on any of that?
Is the benchmark open calculator?
Yes, the benchmark will be all calculator active. Yes. Okay. Okay. So let's turn over. So of course, we've now taken a function and its graph. Now we're going to take the graph of a function and make its function. Okay. So we're going to take the graph and make its function up. Okay. So we've got this thing here, g of x equals a times b to the x minus h plus k. Okay, and we want to come up with this function for this graph. Okay, so first thing, we have to be given what b is. So here we're told that b is 2. So right away I can say, aha, g of x equals a times 2 to the x minus h plus k. Okay. Okay. Let's see, some other pieces of information. Well, we also know what k is, right? We know k based on our horizontal asymptote. The horizontal asymptote is normally at 0, but here in this case our horizontal asymptote is at 1. So that means our graph is has been shifted which direction? Up 1, right? If we normally have our horizontal asymptote at 0 and it's shifted up 1, that means our k has got to be 1. So okay, we know then that g of x equals a times 2 to the x minus h plus 1, like that. Okay. So there's our information. Now, we also have 2 points. Ugh, and they're fractions. Okay, so let me see here about it'd be helpful if we could figure out what that h value is. So let me see if we can think about what that's going to be. Okay, so this first reference point that we get is negative 1/3. Okay, and normally the first reference point is supposed to have 0 for its x coordinate, and so that means it's shifted to the left 1/3 here, since that's the first reference point. So we're shifted left 1/3. So that means that h is going to be x, and then instead, since it's left 1/3, we're going to make it plus 1/3 there, and then plus 1 like that. Okay, so again, that first reference point tells us that it was shifted left 1/3. Normally that first reference point is supposed to be on the y-axis, so it's shifted to left 1/3, which means plus 1/3 there. Okay, and then we can use this second reference point to help us finally solve for a. Okay, that 2/3, where can that go in my equation here? It's an x value, right? And then where can that 5/3 go? And for the y, or where g of x is. So we'll put 5/3 equals a times 2 to the, oh, sorry, thank you, negative 5/3, to the 2/3 plus 1/3 plus 1, like that. Okay? And then we want to solve this equation for a. So, what can we start doing here to get a by itself? What can we do here to simplify this sum? There's our a. We want to get that by itself.
Simplify the exponent.
Okay, so yeah, what's 2/3 plus 1/3? It's 1, yeah. So we have a times 2 to the 1 plus 1. Okay, so again, how can we finish solving here? What else can we do to solve this equation for a? Subtract 1 from both sides first, yeah. Okay. Now, negative 5/3 minus 1 is the same thing as saying minus 3/3, right? Minus 1 is the same thing as minus 3/3. So minus 5/3 minus 3/3 is minus 8/3. Excuse me. But that's equal to a times 2. And then, yep, divide both sides by 2. Okay. Dividing by 2 is the same thing as multiplying by 1/2. And so that can simplify to negative 4, okay, over 3. Okay. And so we get the equation g of x equals negative 4/3 times 2 to the x plus 1/3 plus 1. Okay. So probably the trickiest one that we've had to do, right? That's probably the trickiest one that we've ever had to do. Solving, coming up with those equations. Lots of little steps in there. Okay. Let's try another one. Let's try another one here. Okay. So letter B here, we're going to do the same thing for this graph, but now we're going to have B equal 10. So our base is going to be 10. So again, we'll start out with our function here. I'll just use, I guess it says to use, I don't know what it says to use Q of x or anything like that. I don't know. They're calling it Q of x for this for some reason now. I'm just going to say f of x just because that's the same thing. We're just naming the function. Okay, so it's a times b to the x minus h plus k, like that. Okay. But again, what are some pieces of information we know? Well, we're told that b is 10 in the problem. Okay. What's our plus k going to be? Well, again, remember, our normal horizontal asymptote is at 0. This horizontal asymptote is at 6. So it was shifted which direction? Up 6. So we're going to add 6 here. Okay. Normally, that first reference point is on the y-axis, but it's been shifted left 4 units. So, yep, so it'll be 10 to the x plus 4 plus 6 like that equals f of x. Okay, again, we were shifted, so that's the first reference point. And how do I know it's the first one? Well, it comes first from left to right there, okay? That's the first reference point. And so they have just one more variable to solve for here is a. Okay, one more variable to solve for it, and that's a. So we're going to pick this other point here. Negative 10 is the y value.
It has to be another point.
I think it does because I think either point works here. I think either point will work. We'll check that in just a second, but let's just try the second point and see. I'm sorry, yes. Is that better? Okay. So we're using the other point. Negative 10 is the y coordinate. Negative 3 is the x coordinate. So it'll be 10 to the negative 3 plus 4 plus 6. Okay. What's 10 to the negative 3 plus 4? What's negative 3 plus 4?
It's 1.
It's just 1, yeah. So we get a times 10 plus 6. And we solve this simple equation. Subtract the 6 over, so negative 16 equals 10a, and then divide both sides by 10. I'm running out of space, I'll do it over here. So a is negative 16 tenths, which simplifies to negative 8 fifths. And so we finally get the equation here. F of x equals negative 8 fifths times 10 to the x plus 4 plus 6. Okay. Now, Greg, I think if we did check the other one, let's see here. I think the other one would work. Yeah, so you can use either reference point there. It should work. The other one actually might make it a little bit easier because you're plugging negative 4 in for x. So imagine it'd be negative 4 plus 4 would be 0. 10 to the 0 is 1. So it'd be a plus 6 equals 4.4, and then you just solve from there. Yeah, that might be better. Yeah. So either point there, folks. Either point can work. All right. Let's do one more. Let's do one more of those, and then I'll talk to you about exponential. Well, yeah, exponential growth functions too here real quick. And that's going to be easy because that's on the calculator. All right. Uno más. One more. Ugh. Okay. So again, starting out, f of x equals a times b to the x minus h plus k. Okay. So again, let's see here. Our k. Normally our horizontal asymptote is at 0. Here horizontal asymptote is negative 5 halves. So what does that mean k is going to be? Negative 5 halves. Or minus 5 halves. You don't have to put a plus negative 5 halves. You can put minus 5 halves. That's fine. Okay? Now, also, our first point normally is on the y-axis, which has x coordinate of 0. But this point has been shifted over 3. The first point's been shifted over 3. You okay, Connor?
Yeah, I'm okay.
You had one of those dreams where you thought you were falling. Yeah. So, all right. So anyway, so 3 is shifted over 3. So that means our h is x minus 3 because it's shifted right 3. So we want to show a right 3 shift there. And again, that minus 5 halves for the down 5 halves. And we have one more. We got to figure out what a is. Okay. And let's try using this first point here and see what happens. Let's use this point, the 3, negative 1.
You want to put 2 in for B?
Oh, you're right. Goodness, I got to put the 2 in for the b because we were told these two over here in the directions. Sorry about that. Yes, thank you. Okay. So we'll put negative 1 in for the y coordinate and then 3 in for the x coordinate. Okay. Yeah, I think plugging in that first point is actually going to be a lot better. Because what's 3 minus 3, folks? 0. And what's 2 to the 0 power? 1. And so we end up with just a minus 5 halves. And then how can we get the a by itself here?
Add 5 halves.
Add 5 halves to both sides. Okay, so a is negative 1 plus 5 halves. Well, negative 1, remember, is negative 2 halves. Plus 5 halves is 3 halves. And so we get our final equation there. F of x equals 3 halves times 2 for our b, x minus 3 minus 5 halves. Okay, and there it is. Again, nasty, 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 right? Fractions and just junky, junky, junky looking. But
Other stuff is a lot worse than this.
you think so? Okay. There it is. All right. I got one more thing I got to get through here and show it to you, and then we'll get you guys started on your assignment. Okay, we have some time here too, so hopefully we'll do that no problem. All right. So why do we even bother learning about exponentials? Well, because they actually have a lot of application, especially when you're talking about like investments, like things increasing in value over time or decreasing in value over time. Also like loans and things too. They deal with like exponential growth, unfortunately. Also like populations of bacteria, they grow according to exponential growth functions, or they can be modeled by that. People can be seen to grow at exponential rates too. Populations of people. So lots of applications, okay? And we're going to look at some basic ones here. So an exponential growth function has the form f of t equals a times 1 plus r to the t, where a is greater than 0, and r is a constant percent increase, expressed as a decimal. So r is your percent increase as a decimal, for each unit increase in time t. Okay? So we won't worry about all that there. The base 1 plus r of an exponential growth function is called the growth factor. So this number here, the base 1 plus r, is the growth factor. And the constant percent increase r in decimal form is called the growth rate. So find the function that corresponds to the given situation, then use the graph of the function to make a prediction. Okay? So Tony purchased a rare guitar in 2000 for $12,000. Experts estimate that its value will increase by 14% per year. Okay, now of course that's hard to actually predict, right? If you ever do any sort of investing in the future, one of the key phrases that the website or the broker should at least tell you is that past performance does not predict future results. So just because maybe in the past the value of this guitar was growing 14% per year, no one can guarantee that its value will grow at 14% per year. That's good and bad news. The good news is maybe it'll increase at a higher percentage per year and you'll get even more money back when you go and try and sell it later. Or it's bad news if the value does not increase that much per year. Sometimes the value can go down, right? So it really depends. So anyway, in this case, for this situation, we're just going to say it's increasing at a constant 14% per year. So use a graph to find the number of years it will take for the value of the guitar to be $60,000. Okay? So write a function to model the growth in value for the guitar. So here we start with A, which is the initial price of the guitar, and we're going to repeatedly multiply by the interest rate. Now, we're not going to multiply by 0.14, right? Because if you take your price and multiply by 0.14, that's just going to get you 14% of the price. We want to add that price on, so we're going to do 1 plus 0.14. Like how you calculate taxes, right? If you want to find the tax of something, you can multiply it by 0.06, but that will tell you how much the tax is. If you want to know like what you're actually going to have to pay at the end, you multiply by 1.06. Okay, so that's the idea there. Anyway, so there's our little function. Starts at $12,000 and it makes it's going to increase at a value 14% per year. Okay, so the t is years. All right, and so we can graph this. Well, actually, they kind of did it for us here, so we can just kind of follow along with that. Okay, and so you can see here they use the trace feature. They trace. You can see that as they trace, they get as close as they can to that 60,000, and they see it's going to be about 12 years, a little bit more than 12 years, or 12.29 approximately. Okay, that's estimating. They could have graphed a horizontal line at 60,000 and then done the intersection point. That's another way to do it too. So that's another idea. Okay. And for the second one here, letter B, at the same time that Tony bought the $12,000 guitar, he also considered buying another rare guitar for $15,000. Experts estimated that this guitar would increase in value by 9% per year. Determine after how many years the guitars will be the same amount. Okay? So in this case, if this guitar is increasing at 9% per year, and it started at 15,000, what's going to be our A value here for the function for this second guitar? What's the A value going to be? What's that A value? It's going to be 15,000, right? That's our initial amount. Just if you look up here, right, the A value is 12,000. Here, our starting amount is 15,000. And then it's going to be 1 plus, and what's our interest rate here? 0.09, right? 9% of the decimal is 0.09. Don't put 0.9. What's 0.9 as a decimal? Or sorry, what's 0.9 as a percent? 90. So yeah, don't put 0.9, put 0.09. Okay? And so then we'll add the 1. So we have 15,000 and then 1.09. Notice here that they don't simplify this by multiplying the 1.09 times 15,000. Why can't we put these two numbers together? What's the problem with putting these two numbers together? Why can't we do that? Why do we have to leave it like this? Yeah, 1.09 has an exponent, and so we can't multiply the 1.09 times the 15,000 yet because we have to first raise it to whatever this exponent is. Okay. So when we graph this one and we graph this one, we can find the point of intersection, and you can see it right there. After about 5 years, the two guitars will be the same amount of money, and they'll be both worth around $23,000. Holy cow, right? Don't you wish you had a guitar you could sell to someone for $23,000? All right.
You should find a sucker willing to buy a guitar like that.
You know, I don't want to call someone a sucker that would buy a guitar for something like that, but you know, yes, I'd be willing to bet if you go on eBay, you know, can't do it in here in school. But what's that?
That's going up 9% each year.
That's right. It'd be nice to be able to even be guaranteed something like that, because again, no one can guarantee the value of an item after a certain amount of time. That's the problem. You just don't know, Jordan. Yeah. So, if someone can guarantee that kind of stuff, then, I'm sorry. There are some things that guarantee certain percent increases per year. For example, your bank, right? If you have money in a savings account, but your interest on your savings account is low, and the reason why they make it so low is because they guarantee that interest rate. Okay, if you want something that's a higher interest rate, well then it's more risk, and that's the idea.
High risk, high reward.
That's the point, right? But they also say high risk, high chance of losing some money too, though, right? Higher chance. So, anyway, here's what I'm going to have you guys do. Okay, starting on page 643. Okay. For your assignment. Okay. Yeah. Numbers 1 through 4. You'll just be describing transformations there. It also says determine the domain, the range, and the y-intercept. I'm just going to have you just describe the transformation. That's it. Okay, for 1 through 4. Don't worry about the domain and the range. Okay, just because that makes them a lot longer that way. Okay. And then I'd like you to try numbers 11 and 13. Sorry, 11 and 12. I apologize. I'm going to change that up because I like yellow there. Okay, so 11 and 12 do the domain and range too, but you can also use your calculators. Okay, to help you with graphing those. So that's just graphing. Okay. Then I'd like you to try number 18. And number 20. Okay. So 18 is going to be writing the equation. 18 is going to be writing the equation, so that's that f of x equals a times times b to the x minus h plus k. And then this one's going to be the exponential growth f of x equals a times 1 plus r to the t. Okay? So several different kinds of problems in there, but you have some time to get started on it now, so why don't you do that, and then I can come around and help you get stuck on something. Okay? So give that a try. Okay.
Is that a Finding Nemo type?
No, it's actually Yoda. I know, look, it's supposed to be under the sea or
Yeah,
something
from
like
here it
that.
looks like the water. Oh,
But
now
no,
I
you
see
got
it.
yeah, it's very colorful for
Because like from way over there, like
yeah.
it
The
looks like
swamp.
the ocean.
Yeah, it looks like it's under
It's
the
the
water.
swamp.
Right, exactly. But the swamp, I mean, in the movie, the swamp was not this colorful. It was very
No, it wasn't.
dark
It's
and
like dark and
drab.
brown.
Yeah.
Well, you gotta make the colors pop.
Um.
You don't want to wear like brown, a really
Right,
weird
exactly. It's
brown,
not very
brown tie.
Exactly. It's just not very exciting. So, it's a toss up between probably Empire or Jedi.
You're saying what?
Accuracy or marketability? You gotta choose one.
Right, exactly.
Can I just get water?
Yeah.
More water.
The new one, if I had to rank them, it would probably be like, again, Empire, Return of the Jedi, 1 and 2. 3 would be A New Hope, the original Star Wars. 4 would probably be Force Awakens for me. 5 would be Rogue One, and
then
Your last one is episode 1, isn't it?
probably.
It's the most boring one.
I'd probably go Ren to the Sith, it basically reverse order prequels, so Ren to the Sith, Attack of the Clones, and then.
Well, yeah, it's 'cause they're all like gradually
Phantom
less
Menace.
boring.
Unpopular opinion, I like the space politics.
What's that?
Unpopular opinion, I like the space politics.
Did you?
Yeah, I thought that was neat. I thought like, oh, that's like a regular world.
No, I get what you're saying. For me, I felt like it wasn't.
Nobody really went to Star Wars to see some edgy
I
film
mean,
talk
yeah.
about
It felt
sand and
un-Star
space.
Wars to me.
It
though.
did. It's.
Like that'd be more like a Star Trek
I was
to me.
like,
Kind of.
You don't wanna
oh, that's
watch-
kind of neat. It's just like regular business,
Right.
you know.
Yeah. No, I hear you, and I think because, and again, also you have to understand, I was so hyped for that movie
Oh, yeah.
because it had been
Everyone was.
like 20, 30 years since the last one was made, and so yeah. And then
I don't
it just.
think that George Lucas cared. He was laughing all the way to the bank.
Yeah, I don't know. I mean, at some point he really did have passion for this kind of stuff and really cared, and then I don't know what happened. I think sometimes if you become too isolated, you kind of like become strange, and I think that's what he kind of did. I don't know.
That's a cool character design, though.